Chapter 4, Section 4 deals with concavity and curve sketching. So the last section, we learned about how to find the vertices, whether it's maximum or minima, the extreme points, and whether it's positive and the slope is increasing or decreasing. As our first example showed on a cubic function, here we have a maximum, here we have a minimum. This half of the curve is what we call concave down, because it's, say if you take a bowl and put it upside down, it's concave down. Here we have the curve, the bowl going up. So this is called concave up, or it's commonly called convex. You notice whenever you're concave down, you have a maximum. Whenever you're concave down, you have a minimum. I mean, concave up is a minimum, concave down is a maximum. So how do we find the concave numbers? Well, that's what I'll tell you. There's a point inside here, somewhere between there. It's called the point of inflection, which I'm going to call a POI, is the point where the graph changes concavity. From concave up to concave down, or concave down to concave up. So what do we know so far? If it's concave down, what do we know? It's a maximum, which what? Now, how to relate to the first derivative? Any words, any words. How do you know it's a maximum? Yeah, to the left, the slope goes up and then changes down. Yeah. The first derivative is positive, then it changes to negative. That tells us we have a maximum, which means it's concave down. It's concave up if we go from going in negative, then it changes to positive. Then we have a min. Yeah. Right. So that's what the first derivative is telling us. It's the change of the curve. There's a slope. What would the second derivative tell us? The change of slope. Remember, the first derivative is slope. The second derivative is a change of the first derivative, or the change of slope. it tells us the concavity. In other words, if the change of slope, because remember, it's going from up to down, that's the change of slope. If the second derivative is positive, then it's concave up. If the second derivative is negative, in other words, the graph looks like this, or the graph looks like this. Because think what it says. It says the rate of change of the slope is positive. It's going up. The rate of change is negative, it's going down. So what happens when it's zero? It's neither concave up, concave down. It's the point of inflection. So we know exactly at what point it stops being up to starts being down. If you think about it, like in pilots when they fly airplanes, when they're pulling up, and then all of a sudden they start going down, at what point do they have to pull back up before they hit the ground? The moment they start pulling back up, that's the point of inflection. The roller coaster, it can't be going down forever. It eventually has to start going up. The slope of the track has to change. And that's what the point of inflection is all about. So let's look at example 1. Find the intervals in which the following functions have concavity. Y equals x cubed and y equals x squared. Find the intervals in which they have concavity. So what do you think we have to do? It says again, find the intervals of concavity. In order, since it's saying concavity, what do we have to find? The second derivative. Whenever you see concavity, we know it's second derivative. So the first derivative is 3x squared. The second derivative is 6x. So what's the interval where it's concave up, concave down? So concave up is where the second derivative is greater than 0. What interval makes 6x greater than 0? All positives from 0 to infinity. Where is it concave down? And all the negative values. So what this means is concave down from all the negative values. What does concave down look like? Like a bowl. Does it have a point of inflection? Six x equals 0 when x is 0. So at that point, that's your POI. So it's downward, it's concave down on the negatives, it's concave up on the positives. That's what it tells us. The second one, the first derivative is 2x, and the second derivative is 2. It's a constant. Is it concave up or concave down? Is 2 positive or negative? So it's concave up. So we know since it's a constant, in the entire domain, it's concave up. That's what it looks like. There is no point of inflection, so it doesn't change. It's not negative, it's always positive, so it's always concave up. I see the difficulty you can get with this process because we're always thinking in the first derivative or the regular function. This is telling us the shape of the curve. Is it bending down or is it bending up? Since it's always positive, it's always bending up. Don't worry about the slopes. It's always going to be concave up. Example 2 then. Determine the concavity. Of y equals 3 plus sine x on the closed interval So what do you have to do here? Yep. Since we're dealing with concavity, let's find second derivative. So what's the first derivative? Yeah, because that one goes to 0, so we have cosine. The second derivative, negative sine. Very good. Since our period is 0 to pi, what can we do here first? First thing to do is find the point of inflection. Set the second derivative equal to 0. So at what points is negative sine x equals 0? In that interval. Think of the sine function. Well, in the unit circle, sine is the y value. Where is the y value 0? It's here, here, at 0, at pi, and at 2 pi. The y values are 0. So we know the points of inflection are at 0, negative pi, or at pi, and at 2 pi. But the endpoints cannot be points of inflection. The graph of the sine looks like this. You can't have a point of inflection in the past because remember, point of inflection is where it changes direction. Since those are endpoints, we don't have points of inflection. The only point of inflection we have is at pi. So our PI at x equals pi. Let's look at this in a graph form. How would this graph look? What is the purpose of this 3 right here? It's a vertical shift. So we draw the sine function and raise it up 3 points. So the sine function starts at there, pi over 2, pi, 3 pi over 2, and 2 pi. So this is our sine function. Raise it up 3. So 1, 2, 3. So there's our new x-axis. We have to go up 1 and down 1. So it's here, here, here. So this is our graph. There's the original x-axis. Now we shift it up 3 spaces. Our first derivative function. What is that one going to look like? What does negative sine x graph look like? At 0, it's 0. At pi over 2, what is sine? 1, but we make it negative, so it's negative 1. At pi, it's 0, negative. So the first derivative tells us this. Why is this important? Because you notice on this side of pi, since pi is our point of inflection, what's happening? When x is between negative pi, from 0 to pi over 2, what's happening? Is actually decreasing there and increasing there. So is it concave up or concave down? Well, the graph says it's concave down. Why? Because it's negative. It's the opposite. Then our point of inflection, and then the rest of our graph. Because remember, we're talking about the concavity of this graph. It's concave up from pi over 2 to 2 pi. It's concave down from 0 to, I'm sorry, pi, to 0 to pi. Because that's what we're looking for. Because what this tells us is our graph is concave down from there. Why? Because all the values are negative. All the values are negative of the first derivative. So it's concave down. Point of inflection. Now all the values are positive, so it's concave up. Remember, second derivative, not first derivative. We're not looking at the first derivative. We're looking at the second derivative, not the slope, but the concavity. All the concavity here, everything, this is the second. Since all of them are negative, it opens down. Since all of these are positive, it opens up. And that's all we're looking for right at that point. Find the POI of this function. X cubed minus 3x squared plus 2. How do you find the POI? Second derivative, set it equal to 0. 3x squared minus 6x. 6x minus 6. So where's the point of inflection? Where's it? 1. Set this equal to 0. So 6x equals 6, x equals 1. So the POI occurs at x equals 1. Okay, what good is that? What is that going to tell us? We know at 1, that's when the graph changes shape. It's either going to be open up or down. How do we know what? So let's pick a value. Let's say 0. Plug it in here. What do we get? At 0, what do we get? Concavity, I mean. So here, it's going to go down. The concavity is going down. Afterwards, let's say 2, it's going to be positive, so the graph will look something like this. It's going to be difficult to get away from thinking about slopes, because we've been dealing with first derivative for 5 or 6, 7 weeks now. Now we have to think of second derivative. We have to think of the shape of the curve. So at this side, at 1, I mean at 0, not this point, but the second derivative. We know we have a point at 2, that's the intercept, but it's going down. Where is the vertex at? If this is concave down, this is concave up. This has to have a maximum somewhere. Where is the maximum at? How do you find max min? First derivative. So we have 3x squared minus 6x, set it equal to 0. Oh, minus 2. Take the first derivative, set it equal to 0. They both have a 3 in common. They both have an x. So since I took out a 3x, I divide it by 3x to see what goes inside the parentheses. The 3's cancel one of the x's. So the maximum minimum points occur at 0 and 2. So what this tells us is our graph will look like this and like this. We have the POI happens at 1, and we figure out where it happened, where that point is. So see how we're putting the graph together? We have the point of inflection. We have the maximum minima. We have the y-intercept. We eventually find the x-intercepts. Let's look at example 3. Where's example 3? What was example 3? Yeah, example 4. Find the POI. POI is the second derivative. So what's the first one gonna be? What's the power of the first derivative? Because you subtract 3/3. And the second derivative? Five thirds times 2/3 x to the power 1/3. Or so where would the point of inflection be there? What's the only x value we can't use? We have limits with problem with. We can't use 0. First off, the equation cannot be set equal to 0 because the top is a constant. But remember when we did critical values? When you have fractions, critical values are when the top is 0 or if the bottom is 0, or asymptotes. So our point of inflection is where x equals 0. That's where change occurs. Example 5. Find the POI of I know what you're going to say. If I ask you where is the point of inflection, what would you say? I know. Normally, we would do this. So we're saying that x equals 0 is a POI. And why not? Because in order to be a point of inflection, what has to be true? So let's look at this. In the point of inflection, so if we plugged in -1 and we plugged in +1, if we plugged in -1, what is the answer? +12. So it's concave up. If we plug in +1, what do we get? +12. In order to be a point of inflection, you have to have a change of signs on both sides. One side of the point of inflection has to be positive, one side has to be negative. If they're both positive, that means it's positive everywhere. And that's exactly what this graph looks like. So again, now we're going to the definitions of what point of inflection is. Point of inflection occur whenever it changes concavity. If it doesn't change concavity, there is no point of inflection. It's whatever that common concavity is to both sides. What's that? No. There is a point of inflection at 0, but it's not really. It's not a point of inflection because point of inflections only occur if you have opposite signs on both sides. Because here you have the second derivative is negative, and here you have the second derivative is positive. But in this one, the second derivative is positive on both sides, so there's no point of inflection. There's no change, no curve in the line. So I would say that no POI here. You say, yeah, but I got the second derivative set equals 0. You did, but it's not really a point of inflection, so there's no point of inflection. That question goes more on definition than it does on application. Example 6. The graph of y equals x to the power 1/3 has a point of inflection at the origin. Why does it have a point of inflection at the origin? What do you have to do first to find the POI? Yeah, let's find the second derivative. So it's 1/3 x to the power negative 2/3 negative 2/9 x to the power negative 5/3. Is 0 a point of inflection? Remember, how do you test point of inflection? Let's try values on both sides. Let's try -1 here and +1. So we have -2. And this one is -2/9. In order to have a point of inflection, these two numbers have to have different signs. So in this one, -1 to the negative 5/3. So -1, the cube root of -1 is what? And if you raise it to the 5th power, it's still -1. So we have -2/9 times -1 makes it +2/9. So on this side, it's positive, concave up. On this side, well, this is always going to be positive. So the answer is -2/9, which is concave down. So at 0, we have a point of inflection. And we can see that. From the library of functions, what does the graph of the cube root of x look like? Here you have concave up, and here you have concave down. So 0 is the point of inflection. As long as the numerator is odd, it'll remain like that. If I put a negative number in there, it'll stay negative. If I put a positive, it'll stay positive. But if I would have had x to the power 4/3, because now this fourth power would make everything positive, I would have that kind of graph. It would always be concave down. So again, it's very important to look at the patterns in referring it back to the library of functions. Example 7. The particle moving along a horizontal coordinate line, positive to the right, with a position function s of t is equal to 2t cubed minus 14t squared plus 23t minus 5, where t is greater than or equal to 0. Find the velocity, the acceleration, and describe the motion of the particle. Let's refer back to chapter 2. How do we find the velocity? First derivative. So the velocity at t is the first derivative of our position function, which is 6t squared, 28t plus 23. And the acceleration is the first derivative of our velocity, which is the second derivative of our position, 12t minus 28. So what can you tell me about the position, the movement of this object? What will the first derivative tell us? This one? Should be 22. Thank you. Thank you. I don't know where I got 23 from. So what do? Where is this stuff going to come in play for us? So what's the first derivative going to tell us? It'll give us the intervals in where it's increasing, decreasing. So what do we do with that number? What do we do with it? What's it going to be? Can we factor it? Can we do anything with it? Well, they're all even. We could take out a 2. Let's see about factoring if it's possible. So we have 3t 3t. They're both the same signs. They're both going to be minus. Take the first and the last term. So 3 times 11 is 33. What times what is 33? When we add them, we get 14. Yeah, 11 and 3, 11 and 3. So on the second one, we can factor out a 3. And we just get rid of that 3, delete it. So there's our factor. So what is this going to help us with? If we set both of these equal to 0, that'll find us what? That'll find us our vertex. So these are our vertices. The location, the x values of our vertices, they're critical points. So at 1 and 3 2/3, we look at these intervals. So we use 0 here, use 2 there, and use 4 here. What are those going to be for? Why did I just do that? To see where it's increasing, it's decreasing, right? So now we plug them into our first derivative. So first derivative at 0, first derivative at 2, and first derivative at 4. And we can go ahead. This is our velocity. We can go ahead and use this equation here. Remember, all we're looking for right now is whether it's positive or negative. The number is not going to be important to us. But later on, we say the bigger the number, the more steep it is. So at 0, we have negative 22. So it's negative 11, positive 22. So we have 2 times 0 minus 11, 0 minus 1. So it's 22. So we have 2, 3 times 2 minus 11. So that's 1. 6 minus 11 is negative 5. So it's negative 10. So this part's going down. This part's going up. Two times. So we have the shape of our curve now. So what does this tell us? Remember, this is velocity. The velocity is positive, the velocity is negative, the velocity is positive. What is, if velocity being negative, what does that mean? Or does it mean it's going backwards? Because position is neither really positive or negative, it's direction. It's going left and going to the right. So from here, we're going increasing till we get to, we're actually increasing till we get to -5. And then from here to 1, we're decreasing and then increasing again. That's our velocity. Increase, we're actually increasing opposite direction. Okay, so what's the next derivative going to tell us? The acceleration. And it's going to tell us further of where the shape of our curve. Because we have the basic idea of the curve. Where is the point of inflection? Where does it change direction? That's where the acceleration comes in. I wouldn't have that. So we have our velocity, which is at 6t² minus 28t plus 22. The acceleration is at 12t minus 28. Set that equal to 0. Divide by 12. Two goes in there, 14 and 6. 2 goes in there, 7/3. 2 1/3. So our point of inflection is at 2 1/3. So is it really a point of inflection? Does it change signs both sides? So what happens here and what happens here? So at 0 and at 3. 12 times 0 minus 28. 12 times 3 minus 28. -28. Yeah, since it has different signs, then so it's looking like this. The concavity. So that's what it's telling us. It's telling us the velocity is telling us if it's positive, it's going to the right. If it's negative, it's going to the left. And our change occurs at 7/3, or 2 1/3. Let's see the next one we did that. We talked about that. Yeah, and the next examples are all sketch the functions, the stuff we've been doing, because we're out of time. And we'll pick up from here next time, because I'm looking at some of these examples, and they're rational examples with ease and everything else. So we'll pick up from here next time. All right. Happy Easter, everybody. Or happy long vacation.